Hello all, we are going to look at section 16.3, which is double integrals in polar coordinates. So we'll do a quick review of polar coordinates if it's been a little while since you've looked at them, or even if you've never looked at them before, they're not too terribly difficult, so don't worry. It's just going to be another way for us to write our points in the coordinate plane, and it's related to trigonometry. So even if you haven't seen them, it's pretty familiar. You've probably seen something like it. Then we're going to integrate over polar regions, and then we're going to convert integrals from rectangular coordinates to polar coordinates. All right, so first a quick review of polar coordinates. So like I said, it's really just a way for us to talk about where a point is in the XY plane just in a different way. So what we're used to doing is looking at, the XY coordinate. And x is how far away we are from, so distance, x is distance from the y-axis. It's how far we go left or right. And then y is our distance from the x-axis. It's how far we went up or down. And we get to this spot P right here on our graph, and we say that that point, we reference it as x comma y. So another way we can look at getting to that point is that we go some angle from the positive x-axis. So theta is an angle made, oops, made with the positive x-axis. So just like how we make angles in trigonometry. And then r is a distance that we go from the origin. So r is equal to the distance that point is from the origin. And so a second way that we can talk about that same point is with r and theta. And we always put r first and theta second. So what's nice about this is that you can think of, theta starts with a t, so it's still in alphabetical order. That distance we are from the origin is first, and then that angle is second. And these, x and y and r and theta are related, and they're related in ways that, I'm sure that we're familiar with, that we have created a right triangle here, and x squared plus y squared is equal to r squared. And also x is equal to r cosine of theta, and y is equal to r sine of theta. Those just come from our trig ratios, that cosine of theta is our adjacent side over our radius, and sine of theta is our opposite over our radius. And then you can solve those for x and y. So again, these are probably things that you saw in trigonometry. You may or may not have called them polar coordinates, but hopefully these are things that you're familiar with. So, when we talk about a point here in polar coordinates, we talk about 2 negative 2 pi over 3. So O there is the origin. So, basically what we have here is the xy plane. And so here's the axis. There's the x-axis, there's the y-axis. And so what we're doing when we go to this point to negative 2 pi over 3, we go an angle of negative 2 pi over 3, and that's going to go backwards because it's negative. And then we go a distance of 2 out that angle, and then it gets just to our point. If we were curious of what that point was in rectangular coordinates, we could totally find that. The x value would be r times the cosine of that angle, and y would be 2 times the sine of that angle, and x in that case is negative 1. Y in this case is 2 times the negative square root of 3 over 2, or negative square root of 3. So this point is the same as negative 1 negative square root of 3 in rectangular coordinates. So just two different ways to talk about that place on our graph. And then just, a quick thought of, what does the graph of r equals 3 look like? So r equals 3, this is telling us this is all the points 3 units from the origin. So this is actually a circle with radius, oops, I can't spell radius today. A circle with radius, whoa, and I need to be not the eraser, there we go, with radius 3, centered at the origin. And if you think about that equation, r equals 3, that is a much simpler equation than how we normally write the equations of circles in rectangular coordinates. Notice this is exactly r squared, because x squared plus y squared is equal to r squared. And that's a circle with radius 3 that's centered at the origin. So it's kind of nice. It looks like a little linear equation, but it's talking about all of the points that are on that circle that are 3 units away from the origin. If we were looking at our other question here, what does the graph of theta equals pi over 4 look like? This would be sort of a half line starting, oops, I cannot spell today, starting at 0, 0, and then going out at an angle of pi over 4, which is 45. Whoa, getting too close to the edge. Nope, it's not going to let me right there. So an angle of pi over 4, and pi over 4, that's 45 degrees. So essentially what that one looks like is it is that line. It is all of the points that make an angle from the positive x-axis of pi over 4. So it's everything on this line, that little half line. Okay, so hopefully those are understandable. So let's take a look at what it is that we're going to do when we're looking at regions that we're going to define in polar coordinates versus rectangular coordinates. So again, we want to be able to look at regions that are defined differently, and they're not just rectangular or even made by, our sort of rectangular regular old functions. So these are going to be sort of more circular functions or arches, regions, I mean, that we're going to be taking a look at. So the idea is here's our region that's sitting in the xy plane, and we're going to integrate some surface restricted to this region right here. So we're going to find the volume above that sort of like part of a, almost looks like that looks like part of a donut. And the regions can be different. We'll look at some different ones that we can have. So that's the bottom of our volume, and then the top is the surface, so it's the volume in between that region and our surface. So what we're going to do to take our integral is, like we always do, is we're going to take the region and we're going to divide the region into smaller rectangles. And again, I cannot spell today, rectangles. And I'm going to put rectangles in quotes. So this shape right here, this is a polar rectangle. And with this region, we've got our radius is in between A and B. So there's our lower limit for our radius and our upper limit for our radius. And then our angle is going to be in between alpha and beta. So there's our lower limit for our angle alpha and our upper limit beta. And this is going to make it looks more like I said, kind of like a slice of a pie, with maybe a bite out of the front of it. But that's what we call a polar rectangle. That's why we kind of want to put it in. We can put that rectangle in quotes. So we want to look at these sort of smaller polar rectangles. Now, the interesting thing about these little small ones is when we've got a little small one like that, the smaller we make it, the more that it actually looks like an actual rectangle. So let's think about it as an actual rectangle, because if we make those smaller and smaller, that sort of arch that it's making on the top, kind of that outside edge, that arch that we're getting here and there, that's going to get straighter and straighter because it's not going to be very big. So let's take this sector here and blow it up, this little rectangle that we've got here. Okay, so blowing it up it's going to be, it's still going to have a little bit of a curve to it, but it's going to look like that. And it's going to come out from the origin like that. And it's going to have some sort of change in our angle, some sort of delta theta, so change in our angle. And this little bit is going to be our change in our radius, right? So like we're used to like how big we made those radius slices, same with like how big we made our little angular slices. And so this rectangle, so the area of a rectangle, again, cannot spell today, that is going to be equal to the length times the width, right? Well, the width, we could view that as our delta r. Well, let's make the space here. The length, so that's be our width. Our length here, so that's the length. That's going to be the length of this arc. And if it's been a little while with your geometry, arc length is your radius times your angle. So radius times the angle, so our radius, so how far we've gone out. So in this case, it would be sort of radius sub I. So how far did we go out here? How far did we go out? And then times what our angle is, which in this case is delta theta. So we're going to have our little r sub I times delta theta, and we're going to take all of those little areas, we're going to add them up, we're going to have summations. And so what this is going to do to our integral in rectangular coordinates is that it's going to take that region that we have and change it from being just a rectangular region, is that we're going to go from alpha to beta. And we do usually do the angle second. It's not necessarily, you don't have to, but they usually introduce a pi as part of our constant term, which is moderately annoying. So we usually do the angle second. Um, and then we're going to go from A to B on our radius. We're going to take our rectangularly defined function and we're going to replace x with r cosine of theta. We're going to replace y with r sine of theta so that we're going to have our function in polar coordinates. And then the area of our rectangle, which is our dA, that's the area of those little rectangles that we make in our region. Notice what that's going to be. We're sort of used to it being dy dx or dx dy. Here it's going to be an r, which that's really interesting. We're introducing an r into this. And then dr and d theta, because our delta r and our delta theta turn into a dr and a d theta. So that's what our new integral is going to look like. So when we change from rectangular to polar, the big thing that's going to change, yeah, your limits of integration are going to change. Your function's going to be in terms of r and theta, but our limits of integration, not our limits of integration, our differentials there on the end, our dx, dy, those are going to change into an r, dr, d theta. Okay, so let's convert the following to polar coordinates, not coordinated, and evaluate the integral. So one of the first things that I do with this is sketch that region that they want me to integrate over. So, in my polar coordinates, because again, the outside differential is dx, so that's telling me my outside limits of integration are going from 0 to 1 for x. So let's maybe put that right there. And then for y, we're starting at 0, and then we're going to the square root of 1 minus x squared. So what is that? Square root of 1 minus x squared. Well, you might know what this is, but if we square both sides, we're going to see, oh, we've got a circle. So we're going to be integrating over the region a little quarter circle here, because we're just going to go from 0 to 1. on x, and we're starting at 0 for y. So it's going to be that little quarter circle there. That's a really ugly looking quarter circle that I drew. You can draw a little bit of a better one here. Quarter circle, nah, not much better. So with this, we want to look at what our limits of integration would be in terms of r and theta. So r is starting at the origin and going out until it hits the edge of that circle. So r is going to go from 0, because if you're sitting at 0, 0, you're 0 units from the origin, and it's going to go out to a length of 1. Theta is again how much of an angle that we make starting from that positive x-axis. So theta starts with an angle of 0, and it goes to pi over 2 because it goes to the positive y-axis. So those are going to be our limits of integration. Already those look better. They're numbers because this thing sure is ugly as a limit of integration. So that changes our limits of integration. We're going to go 0 to pi over 2, 0 to 1. And again, we usually integrate with respect to r first and theta second. It really doesn't matter. You can switch those if you want, but we usually do r first. So we also need to take our function here, our e x squared y squared, and we need to change that into polar coordinates. Well, one of the things that's true, if we go back here, that x squared plus y squared is equal to r squared. So anytime we have x squared plus y squared, we can replace that with r squared, because that is true. So this is e to the r squared, e to the r squared. And then we also need to change our differentials here on the end from dy dx to r dr d theta. So again, they always change that, always adds that r in there. And again, where that comes from is back here. It comes from finding this length of that arc there, because that's our radius that we go out times the angle that we've made. Okay, so now if we evaluate our integrals, let's go back to a different color here. So again, we want to do that inside integral, the integral from 0 to 1. Oops. E to the r squared times r dr. We can use substitution on this. And so we get 1/2 du is equal to r dr. And we actually do, if we change the limits of integration, it would still go from 0 to 1. I enjoy that. So we get e to the u du, so e to the u from 0 to 1. So we are going to get, oops, you know what? I forgot something. I forgot our 1/2. Oh no, 1/2. 1/2 e to the u. So we get 1/2 e to the 1 minus 1/2 e to the 0. So that's 1/2 e minus 1/2. So again, we can plug this back into our double integral as our inside integral, and then we've got pi over 2, and then we're taking the integral of 1/2 e minus 1/2. Those are all constants, d theta. So again, we are plugging this guy in here for this whole big inside integral. And so again, this is all just a constant, so all of this gets multiplied by theta. Theta goes from 0 to 2 pi. And so we're going to get 1/2 e minus 1/2 times pi over 2 minus 0. And if it helps, I didn't mean to have these kind of run into each other like that. Sort of our inside integral off to the side there. And so yeah, we get, let's see, pi over 2 times 1/2 e minus 1, or pi over 4 e minus 1. And we could be good because this is a volume. This is units cubed if we wanted to. All right, let's do another example. Okay, let's convert the following to polar coordinates. Again, I did it again. Let's cut and paste. Oops, not that d that I want to get rid of, that one right there. And evaluate our integral. So again, we've got our function, square root of x squared plus y squared, and then we've got our region that they're giving us in that notation that we saw in class the other day. So let's take a look at what this is saying. So this is saying that we've got x squared plus y squared is greater than or equal to 1 or less than or equal to 9. So kind of here's our two limits. squared plus y squared is equal to 1, and x squared plus y squared is equal to 9. Those are both circles. This one has a radius of 1. This one has a radius of 3. So we are looking at, there's a circle with radius 1. That's probably the best circle I'll draw all day. There's our circle with radius 3. So we're bounded by that region, but we're also bounded by this part right here that says y has to be greater than or equal to 0. So that's going to have us look at just this upper part of our donut. So it's literally half of a donut. And then if we think about what our limits of integration are going to be in terms of r and theta instead of x and y, we're looking at r going from 1 out to 3, so starting at 1 going to 3. And again, notice that's a much nicer limit of integration. We don't have a function in here. Things are much nicer. In terms of our angles, it's going to start at 0 and it's going to go until we get to pi. So we're going to go from 0 to pi for our limits of integration for theta. Our function that's here in the middle here, that's in rectangular coordinates right now. Again, anytime we have x squared plus y squared, we can replace that with r squared. Square root of r squared is r. And then our dA, that's always going to get replaced with our r, dr, d theta. So our integral is going to be from 0 to pi, 1 to 3, r times r, dr, d theta. And so again, I do like to take that inside integral and kind of go off to the side and compute that inside integral. So r times r is r squared. dr is 1/3 r cubed from 1 to 3. I will save us a little bit of calculation. This is 26/3. So that 26/3, that's going to be our result from our inside integral. So that inside integral, we can replace it with 26/3, then d theta. And boy, again, we have a constant function. So when we take the integral, we have that constant times theta. And so we're going to get 26/3 times pi minus 0, right? So just 26/3 times pi, and that's going to be units cubed. So the nice thing is it takes something that's pretty ugly looking with a lot of x squareds, y squareds, all sorts of things like that, and makes these kind of back into sort of what we were doing in 16.1, where we've got limits of integration that aren't functions, that are numbers. Everything's a lot nicer. Let's do one more of these. Make sure we've kind of got this down before we practice these in class. So let's convert again. Ooh, cut and paste. You are not my friends today. Convert to polar coordinates and evaluate this integral. So we got a slightly different function here, but let's look at our limits of integration first. So let's start there. So we've got something similar to what we had the last time. We've got x has got to be bigger than this 1 equals x squared plus y squared, and smaller than 4 equals x squared plus y squared. So we've got circles again. This again has a radius of 1. This guy has a radius of 2. So remember, it's always, we've got r squared sitting there. So it's always the square root foot sitting there. So we've got, again, that circle there with radius 1 and our circle with radius 2. All right, what other restrictions do they have on us? They have telling us that y is greater than or equal to 0. So that's telling us that we are using just this part of our coordinate plane. Okay, what else are they telling us here? So then they give us that y has to be in between negative x and positive x. So those are two linear functions, and they both go through the origin. So it's got to be in between those. So if we draw those lines in, there's our two lines there. We've got to be positive x values. We've got to be in between our donut here and in between those linear functions. Actually, let me do a slightly less obtrusive color here. So that's our area that we're going to integrate over. That's our region. So what is that in terms of polar coordinates? So again, if we're looking at the radius here, it's going from 1 to 2. And then our angle is going from, what is that? That's negative pi over 4, and it's going to pi over 4. Okay, so we've got slightly different limits of integration this time. Now we do also need to take this inverse tangent of y over x and convert that into polar coordinates. So remember, y and x, y is equal to r sine of theta, x is equal to r cosine of theta. The r's cancel, we get inverse tangent of sine of theta over cosine of theta. Well, sine over cosine, that's tangent. So we get the inverse tangent of tangent. So that's just theta. So again, what we've come up with is we have that function in there that's kind of annoying, and it would be, very difficult to find the integral of that, well, or at least not the easiest thing to do. And now we're able to change this into polar coordinates and get an integral that's much more easy for us to compute. And so we've got our limits of integration there. We've got our function now in polar coordinates. That's our theta. And then we always have this dA. That's our r, dr, d theta. So now in this case, when we take that inside integral, so 1 to 2 theta times r, dr, um, theta, it's a constant in this case. We're taking the integral with respect to r, so theta is just going to hang out, and we're going to get r squared over 2 from 1 to 2. Again, I'll save us a little bit of arithmetic. You should get 3/2 times theta. And then if we plug this back in to our double integral for that inside integral, we are going to have 3 over 2 theta d theta. So we're going to get 3 over 2 times 1/2 theta squared. And again, theta is just like any other um, variable, so all the rules of integration still apply. And when we go to plug things into this, we're going to get 3/4 pi, pi over 4 squared minus 3/4 negative pi over 4 squared. And you know what? This is highly unsatisfying because that ends up being 0. So basically what that means is that we've got a net volume of 0. So like sometimes in 252, we get the area under our curve is 0 because sometimes we've got that positive area and negative area. Same thing's happening here. We've got some positive volume and some negative volume, and we add the positive volume and the negative volume together. We get 0. So that's what's happening here.